Excellent. So we can see your screen. So the next presentation is by Yasemin Bekiroğlu, and she will present her work on object shape estimation and modeling, combining visual data and tactile exploration. Yasemin, over to you.
Thank you very much. I'd like to start by saying that, let me see if I can move my slide. Yeah, saying that we all see many different robotic applications being developed, ranging from agricultural robotics to assembly or inspection and maintenance. And most of these require grasping and manipulation skills. However, autonomous grasping and manipulation skills approaching human level is still a challenging goal. One main reason is that robots often need to deal with unknown objects, and properties required to plan grasp and manipulation actions, such as shape, is not then known a priori. And sensory information is needed to extract this information from the environment, and often the first modality that we use is vision. And as you see here in this example, visual data is often noisy, incomplete, and therefore vision is prone to error. And processes before shape extraction, such as segmenting object from background, they are not perfectly accurate due to, for instance, occlusions and noise. Then we can turn to other modalities such as touch sensing, which can be complementary to vision. When we look at, for instance, human skin, we see that we have millions of receptors, and they are sensitive to many different things such as pressure, vibrations, texture, pain, proprioception. And available state-of-the-art sensors are still somewhat inferior to this. For instance, they either provide less information or much lower resolution, as you see in these examples here. When they mostly deliver pressure information, and we can still use this to support visual sensors to a certain extent for the tasks that we consider. We also see from human studies that we combine vision and touch sensing in an optimal way to perceive objects. So we would like to do similar, we would like to equip robots with similar capabilities. So how can we achieve these similar goals? Using a robot can we complement visual data with tactile readings to improve perception? That's the question and the main focus of this talk. Given incomplete visual data like this, as you see here, can we complete it with tactile data so that we could reach to a reasonable shape estimate that we can use for grasping and manipulation planning? So consider a scenario like this, where we see only the front side of the object with a fixed camera, and we don't observe the back side. And we don't have any information about what is available on the back side of the object, what it looks like from that part. And one idea is basically to let the robot touch the unseen areas to gather more information, to gather more tactile observations, so that we can model the object shape better. And here it's also important to choose a very good representation that enables efficiently the subsequent tasks. So can we fit a surface like this, as you see here, the green surface, to visual and tactile measurements, so that we can model the underlying true object shape using this idea. We can basically formulate this as a regression problem. The input would be 3D points from visual and tactile sensors. As you see here, vision data are represented as yellow points, and the tactile data are represented as red points, and they are all in the same reference frame after we apply some pre-processing steps like calibration and registration, etc. And the idea is to map these 3D points to a one-dimensional output value, which will represent the surface that we are after. We can then distinguish different input points by grouping them as follows. We can say that I want the surface points, the points on the surface to evaluate to a certain value such as 0, the points outside the surface which we can determine by fitting or assuming bounding box. We want those points to evaluate to a different value, for instance, to 1, and the points inside can evaluate to another value. So how can we realize this mapping? How can we realize this regression? We can use a probabilistic approach as the data is noisy. And in particular, we choose to use Gaussian process formulation because it gives us a principled way to calculate uncertainty in our estimates. For instance, as you see in this 1D example, we can be very confident around the observations, and as we move away from the observations, our uncertainty in our estimates increases. And we can make use of this property very well in our scenario. In order to use Gaussian processes, we need to make some design choices. We need to choose a covariance function that models that is suitable for our problem, because this will determine the characteristics of our model. We choose to use this specific kernel called template covariance, template kernel, or template prior. And the reason for this was because it yielded very good reconstruction results. And we will make use of this uncertainty in our estimates formulated by the covariance, as you see here, to guide our touches. We will send the hand to most uncertain areas to perform exploration so that we maximize information gain. Here we see examples of how these surfaces change as we add more observations. So green color corresponds to low uncertainty about our shape representation. And the model on the left side corresponds to the initial surface reconstruction with no touches, basically only using initial vision data. And then as we add more touches around the most uncertain areas, here represented as the red regions, our shape can be updated accordingly, and we get more similar results to the actual true object shape. So here I have more examples of how the shapes evolve as we add more and more tactile readings. In this case, we have true object shapes here on the right-hand side, and we assume that our exhaustive exploration has about 54 touches all around the object, and we see that we get more or less sufficiently good results with around 10 to 12 touches. So I have a video showing the whole process. So we had an initial segmentation where we segment out the object point cloud from the background, and then we command the robot to go to the most uncertain area to gather more tactile readings there. And we update our surface model based on the newly acquired readings, and this shows a 2D representation of how the groupings or clusterings look like when we update our surface model. And we had 3 groups of objects: bottles, boxes, and cylinders, and the core point was represented with a star, which eventually goes closer to the right group. And after this touching step, the query point moved even closer to the true group. And I think with about 9 touch, the 9th touch, it's gonna appear even better and thinner. Let me see if I had, unfortunately I can't fast forward this, but yeah. As our results support, we need about 10 to 12 touches to more or less say what the group object belongs to. So to simply evaluate how well the models are, we could extract features and perform clustering of shapes. We analyze different features. Here I'm showing the best performing ones, namely principal curvatures. And as you see, when we build similarity matrix from these principal curvatures, we see that objects are well grouped, and the clustering based on this also yields similar results where we have instances from the same category close to each other. And we see that sufficient well groupings occur after about 12 touches. However, one limitation with this approach is that its complexity grows fast with data size. And there are alternative approximations, and this is a good research area in order to make this computation more efficient and less time consuming. We choose to use a formulation based on using auxiliary input-output variables, namely inducing variables. And using this and based on variational approximation or posterior, we build approximate Gaussian process implicit surfaces. Again, just to have a quick look at the system outline, we reconstruct our surfaces, we extract some features such as principal curvatures or any other feature that you might be curious about, such as Zernike moments. Then we calculate the similarities based on, for instance, kernel-based two-sample tests. And then we perform some basic spectral clustering to understand how well the representations really help us to group similar looking objects together. We analyzed results this time using also looking at different kernels. We added, on top of template prior, we added squared exponential and Matern kernels. And these are results with using based on different kernels. And the best performing one was the, again, template covariance. And as you see here, I'm showing some results based on some synthetic data where we don't really have a lot of noise, but the data is kind of sparse. So therefore, we see some high uncertainty values in certain areas. And we also looked at the distances between the resulting surfaces and the ground truth scans. And we see that, again, template-based representation and reconstruction gives us the minimum distance to the ground truth. We also compared the full formulation with the approximated implicit surfaces. So this is the full, and this is the approximate surface representation. And we see that we can preserve the accuracy well enough, and still the distances to the ground truth also look really similar to the full approximation, which was good enough already. So we are able to preserve the accuracy using the approximate formulation. So we've got a lot of analysis in our study, and here we can see more reconstructions using synthetic data and real data from two different robots. And they show similar characteristics to true object shape, as you see. They are rough approximations, but this kind of representation seem to be good enough for first of all, distinguishing objects from each other, namely categorizing them, and also doing some graph planning, which I'll mention very briefly later on. So we, again, did some clustering experiments where we got similar behavior. After a few touches, we are already able to distinguish different groups from each other, and the quality is good enough compared to exhaustive exploration case. And the data set from this is available. You can download it. We've got real data from two different robots, PR2, KUKA, and a setup with a KUKA arm, Shun hand, and a Kinect camera. We have about 20 objects from 4 categories, also ground truth scans, and we would be curious to see if other people interested and if they got more other results. We also worked on some extensions of this. We looked into how to extend this to exploring environment, and we've got some initial good promising results where you also see here we get some good enough approximations of the environment. And we are currently looking into how to do graph planning based on this representation in a probabilistic exploration way. We've got some promising results and hoping to publish soon. I'd like to conclude by saying that this probabilistic shape models are a good way to represent unknown object shape, and we can refine visual estimates based on adding touches guided by uncertainty in our formulation. And there are a lot of future directions that might be interesting to follow. I'm listing quite a few here, but I'll maybe name a few. I would be interested in increasing the accuracy even more, playing around a bit with the GP formulations and the kernel kernel functions. And it will be interesting to do exploration using two hands, adding maybe geometric priors, making use of topology, non-stationary kernels, addressing the fact that the noise in the data is actually heterogeneous. So you get different levels of noise from vision and tactile data. And category level modeling is very interesting as well. Thank you very much. And I'm curious to hear if you have any questions.